All right, welcome. So we are, get my pen here. Where is my cursor? There we go. Oh, okay, there it is. We are talking about related rates, part 2. Before we talked about how do I find the derivative if I don't have a function in a nice explicit form, but rather part of an equation, sort of hidden inside an equation, and that we do by what we call implicit differentiation. Differentiation, where I simply take the derivative of the left-hand side of the equation and the derivative of the right-hand side of the equation, and they have to be equal to each other as well. And I just have to watch out if the letter of the input variable, we'll call it x usually, if it's not the same as what the variable is inside the square brackets, then I have a chain rule situation that I have to be aware of. And we did an example and showed that we still have the tangent line concept connected to the derivative for these more complicated graphs. Now we want to look at something a little bit more practical. We can look at our problem book and we have some questions here that we can do. The first one I wanted to do was the classic 11.13. Let's zoom in as much as we can here. Hey. 11.13. So we'll see how the this problem works. A rock is thrown into a still pond. The circular ripples move outward from the point of impact of the rock so that the radius of the circle formed by a ripple increases at a rate of 2 feet per minute. So the ripple, as you can imagine, is moving outward, creating a bigger and bigger circle. Now we have to find the rate at which the area, there's an A missing right there, of course, area, at which the area is changing. Of course, as the radius of the circle changes, its area is going to change as well. But exactly how? At some moment where the radius is 4 feet. So let's have a picture and see what this situation looks like. This is our basic kind of related rates question, and then we'll look at variations. So let's draw a circle. So 11, what was that, 13? Well, I just looked at it. 13, there we go. So let's draw a circle. There's my circle. I am going to have to talk about a radius, and I'll call it R. And I'm also going to have to talk about an area A. Now, this circle is moving outward, and the radius is increasing, and therefore the area as well. At some specific point in time, the radius is 4, but in general, the radius is a changing thing. Since this is a word problem, we have to start with defining our variables. So we say let R represent the radius of the circle. What's important here is to realize that R is a function of time. Now, we don't have to define the time variable. We all agree we're going to use a t, but it's not the same kind of input variable we are used to. Technically, time, t, is the input variable. R is a function of that. And so is the area. Let A represent the area of the circle. Now, you don't have to say the bracket portion. I just want us to be aware, because this is our first kind of example, that this A is a function of what? Technically of time. It's a function of time. Now, we can write R of t, we can write A of t, but as long as we keep in mind what the R and the A actually are, we don't have to emphasize the bracket and have too many letters floating around. We don't need them. We just need to be aware that they are in fact functions of time. There is a simple formula relating these two to each other. And most of these questions will have some geometric formula that most of us may know or is easy enough to remember. The area of a circle is pi r squared. So even though these two are related to each other, they are sort of individually changing as time passes. As time passes, the circle is expanding, the radius is increasing, the area is increasing over time. We don't know what those functions are. There's some functions we'll never know. But these two functions change in a connected way according to this equation. Now, the question talks about the radius increasing at a rate of 2 feet per minute. We want to know the rate at which the area is increasing. So we are interested in rates of change here. Rates of change are derivatives. So we want to see the derivative of A, the derivative of R, because those things are what the question is talking about. In order to do that, I'm going to, why am I writing over here? I'm going to write over here. I just had my picture there. We are using implicit differentiation to get those derivatives by taking the derivative of whatever is on the left, taking the derivative of whatever is on the right. But now, in these practical problems, the input variable, as we set up here, the input variable is time. So it's not x, it's t. So it's very important that I have the appropriate input variable in my big D notation. And they will all be t. Practically, things are changing over time, and those are the only examples we are going to focus on. Okay. So now I don't have anything on the left here. The A is just on its own. The big D notation I can just rewrite to a little d notation because it is a little bit better if I don't need to see a fancy inside thing that I need to take the derivative of. It's just the derivative of A. Name it whatever you want. You can name it A prime if you want. But The way I like to write these are with the little d notation, to just out of habit, honestly. You can use any notation for a derivative you want, technically. So that's the left side, not much happening there. The right side, there's something happening. That my derivative is with respect to the t variable. Yet I don't have the t inside the square bracket, I have an r. And r, remember, is itself a function of time. So I have this constant pi, I have this r, which is a function of time, and then I square it. That's a function of a function. Function of a function. The inside function is this radius function that I don't know what it looks like exactly. The outside function is the square function. So if the letters don't match, we have a more tricky situation, really the only one we need to watch out for, and we have to use the chain rule because I have a function of a function. So the derivative of the outside function is, well, the 2 goes in front of the pi just to look nice, and then r to the 1, but we don't write the 1, times, says the chain rule, the derivative of the inside function, which was just the r function. So I'll write dr dt, though any version of the derivative of r would be fine. So here we have what we call the related rates equation, because I have an equation now that relates the rates of change of these mystery functions of time. And that is ultimately what we need to work with based on the information that the question gives me. The question talks about rates of change, which means I need to understand how the rates of change of the radius and the area relate to each other. So the whole implicit differentiation thing, all of this was to get to this equation in the box, the related rates equation. Now this is something that all of these things, the rate of change of the area, the rate of change of the radius itself, they are potentially changing over time. I don't know their detail. I just know they are related like this. So at some point in time, even though these things are changing individually, they're connected in some way. At some point in time, we're given some stuff. We're given, now I look back at the question, we're given that the radius increases at a rate of 2 feet per minute. So that means the rate of change of the radius is 2. Now you can keep track of the units, but we're not going to get messy with units and have it be tricky to convert units and have different units. We're just going to keep everything consistent, so you don't really have to worry about that. We're worried about the math. That is the more difficult thing. Keeping track of units is something easier. So we're given the rate of change of the radius is 2. We want to find the rate at which the area is changing. The rate at which the area is changing. So we want the rate of change of the area. And you see in this related rates equation, we have 3 things that we don't know. Only one of them can be missing, the one we want to find. We're going to have numbers for the other ones. So we need R as well. And that's why they tell me at the instant, at the moment in time where the radius is 4 feet, where the radius is 4 feet. So we're also given the radius is 4 feet. So those are all the things we need in our equation, in our related rates equation. So now you have a choice to make. Not a big choice, but it's a choice that matters to some people. I can go one of two ways. One way is I can look at my related rates equation, and in general, the missing part isn't always going to be just on the left. Actually, no, let me backtrack until we have a more difficult related rates equation. Don't worry about that now. In this one, what we're looking for is already isolated on the left, so there's nothing to do. Now we just plug in the numbers, and we have that the rate of change of the area at this point in time is 2 times pi times 4 times 2. Get out your calculator, find the answer. So if I put in 2 times 4 times pi times 2, it gives us, my cable is stuck here, it gives us 50.2, let's go to 7 if I round it, and that will be square feet per minute. Feel free to test that in the main classroom chat to see how you can do calculations just in the Discord chat instead of a calculator. So we have a word problem that we need to finish with a sentence by saying the area is increasing at approximately 50.27 square feet per minute. And we're done. Let me zoom out a little bit so we can see uh, the whole question. Okay, so the next one that I want to do is sliding ladder, sliding ladder. Number 12. Oh, there we go. No, that's not the one. 11. 11.11. So we have a ladder 5 meters long that rests against a vertical wall. If the bottom of the ladder slides away from the wall at the rate of 0.5 meters per minute, how fast is the top of the ladder sliding down the wall when the base of the ladder is 1 meter away from the wall? All right, so before we worry about the whole question in one go, we want to visualize what's happening here, see what variables we need, and so on. Let me make a new page. All right, so this was 11.11. Let's get a picture going here. Let's put the picture on the side. So I have my building. There's my building. There's the ground. That's assumed to be level. There are some windows in my building. There's a door. There we go, building. Now, this is not to scale. I have a ladder. I'm gonna do a straight line to be clear. there is my ladder. I know that's always 5 meters long. The bottom end is sliding out, the top end is sliding down. I'm gonna have to measure the distance from the bottom base corner of the building to the bottom of the ladder as X. And I'll go from the ground up to measure the height of the top of the ladder, and we'll call that Y. So let's define those. Let X represent the distance to the bottom, let's say, of the ladder. Let Y represent the distance to the top of the ladder. Wordy, but I bank 1 mark easily for any test question. Now, I remember these are actually functions of time for these kinds of related rates questions. Time is passing, the ladder is sliding, these distances are changing. What they are in terms of time t, I have no idea, and we'll never know. We need an equation to connect these two variables. Now, we have a right-angled triangle here, which means x squared plus y squared equals 5 squared, or I can just update that to 25. The 25 is never going to change because the length of the ladder is never going to change. So again, we have a simple geometric formula or equation that gets us our starting point. But there are some things, geometry-wise, that we have to remember. Now the question is referring to the ladder sliding away from the wall at a certain rate, sliding down the wall, as well as some lengths. So there are rates of change involved in this question. So I need to get to a related rates equation, and I'm always going to do that the same way by taking the time derivative of both sides of the equation. My variable for these practical questions will always be time. Now let's do the right-hand side because it's super easy. If 25 is constant, derivative of a constant is 0. Left-hand side, I'll split it up to show that we are using the sum property. Nothing strange is happening here really. Our derivative properties are still what we are using. But now we just have to be careful. I used an x for a variable that's really a function. So this first one, the derivative of x squared, is a function of a function situation. Just because it's x, the letters are not the same. We're going to have to use the chain rule. So the outside function is x squared, derivative is 2x, times the derivative of the inside function, dx dt. Second one is very similar, but I'm a little bit more comfortable with y being a function itself. The little trap potentially was the x. So I have the derivative of the outside function times the derivative of the inside function. And of course, the other side is 0. There is my related rates equation again. So now let's put a box around this one because this is now what we're going to use. Now I like to just now look back at the question and say, okay, what did I know? What was I given? Because I can only have one unknown in this equation. I realize my webcam froze again, but I'm just going to ignore that. So in here, let's do it on the side. At some point in time, actually, no, let's not do it on the side. At some point in time, I don't know exactly when, but they are giving me more information. They are telling me the bottom is sliding away at a rate of 0.5 meters per second, per minute, sorry, 0.5 meters per minute. The bottom, so that is x, changing at a rate of 0.5 meters per minute. So we're given dx dt is 0.5. I'm not going to write the units every time. Our units will always work out. We don't have to worry about that. What else are we given? We want to know how fast the top of the ladder is sliding down. So that's dy dt. Top of the ladder, y, the rate at which it's changing. So we want dy dt. So in my related rates equation, that's going to be the unknown. So I better have a way to find everything else. What else do they give me? Um, the base of the ladder is 1 meter away from the wall. The base of the ladder is 1 meter away from the wall. That means at this point in time, x is 1. So x is going to be equal to 1 at this point in time, because that's exactly what we defined x to be. Now, in my related rates equation in the box here, I'm going to have numbers for everything except the thing I want. And I don't have a value for y yet. I need to find it. How can I find the value for y? Let's zoom out. Not in, out. I can find the value for y by looking at the original equation relating x and y. I can solve for y here or plug in the x value. Let's do it on this side here. So 1 squared plus y squared equals 25. That means y squared equals 25 minus 1, so 24. So y is the square root of 24. Let's go to our Discord MathBot to ask it what that is. So I get 4.89-ish. 4. Ooh. If I round to 2 decimal places, it's really 4.90. Now, I do have to use the original in any future calculation, but whenever I present it, it's okay to round. So the point is now I do have everything I need in this related rates equation. This is where you have two options. One option is, and it's not a right or wrong, it's just a matter of preference. One option is to solve for your unknown in the related rates equation first, which is dy dt. So I'm going to move the term with x's in it to the left, like so. And then I have to isolate dy dt to get dy dt equal to negative 2x dx dt over 2y. And the 2's can cancel. Then, for my specific point in time, I'm going to zoom out. For my specific point in time, I can then plug in the specific numbers. I have my negative, my x is 1, my dx dt is 0.5 over y, which is root 24, and I'll get an answer, which we'll do in a second. Or, actually, let's do it now. Let's do the answer now. Check on your calculator what that answer is. Remember to not use the rounded value for y, but the original. MathBot says negative 0.10 if I round it. Your other option is to plug in your numbers first. So I have my 2 in my related rates equation. I have x, which is 1 in this case. I have dx dt, which is 0.5. I have a plus 2. Y is, whoops, let's get rid of that. Y is root 24. And then I have my missing dy dt equal to 0. Then people can calculate this, people calculate that, and move the numbers around to solve for dy dt. Some people find that having the calculated answers, which I'm not going to bother to do, some people find the numbers less intimidating than the symbolic version of the related rates equation, but you'll see even if I calculate this in pieces early, I'm going to get the same answer, of course. So choose which way you want to do it. It doesn't matter to me. It's all the same in the end. Just don't use rounded numbers early. That's the only thing. So there's only one thing left to do. And that is our concluding sentence. So we have calculated what happens to the vertical distance in terms of its rate of change. So we can say the top of the ladder slides down at a rate of approximately 10 meters per, was it minute? Let's check. Yeah, it was minute. So you can either separate, because this is negative, that means it's decreasing, that means it's down. So you can either separate this negative and give the appropriate word to it, and then put the number over there, or you can say the top of the ladder changes, or the distance to the top changes at, let's not say, let's not say changes. The top of the ladder slides at a rate of negative 0.10 meters per minute. You can choose which one you want. It's a little nicer to indicate the direction in words rather than the reader in general trying to figure out, what does this negative mean? Which way is it moving? You can interpret that negative and then separate that from the number because it's already in the down word. You're not going to say the top of the ladder slides down at a rate of negative zero point 0.1. That is what you should not be saying. So how you write your concluding sentence is up to you. There's some flexibility there for sure. But we've wrapped up our question. Let's zoom out and look at it again.